Okay, so now we're going to look at resonance structures in a little more detail and do a little practice. All right, so I'd like you to start off by drawing the carbonate polyatomic ion with that CO3 -2. So what that indicates to you is that we're going to have a carbon in the middle with 3 oxygens attached, and you get 2 extra electrons to place on there. That's what makes it an ion. Then, once you've drawn the structure, let's think about, like, what's the average bond strength and the average charge that each oxygen has. Pause the video, see if you can draw CO3 -2. Okay, so let's take a look, see what you did. All right, so there were 3 different ways that you could have drawn this polyatomic ion. You could have done it with the double bond located at the top of the carbon and the 2 extra electrons on the ends. You could have done it where the double bond was down here with the 2 extra electrons at these 2 ends, and you could have done it with the double bond down on this side and the 2 extra electrons here and here. So which one of these is correct? Well, the answer is all of them are correct simultaneously. So let's take a look at what happens when those bonds are able to move around. So we end up with a resonance structure that looks something like this, where that double bond could be located here, here, or here, and in fact that double bond is actually being shared among all 3 oxygens. At the same time, those 2 negative charges can rotate around as well following those double bonds. So those 2 extra electrons are also being shared among 3 oxygens. So in this case, the atoms aren't moving, it's the bonds and the electrons that are moving. So what we can do is we can take the average of the charges and average them among the 3 oxygens. So there's a -2 charge, but it's divided by 3 oxygens, and that gives us a -2/3 charge that each oxygen has on average. At the same time, the bonds are a single bond in every location with 1 extra bond being shared among 3 oxygens. So 1 bond, 3 oxygens, it's 1/3 of a bond is its strength. So 4 bonds divided by 3 oxygens is 1 1/3 bond strength. The average bond, average charge of the oxygens, -2/3. By the way, we draw the resonance structure the same no matter what partial bond it has, whether it be a 1.5, 1 1/4, 1 3/4, that doesn't matter. What matters, we draw it the same, but you can calculate what that strength would be. So in this case, overall charge -2, that's being shared among 3 oxygens, -2/3 charge per oxygen. Okay, let's try another. Draw the bonding structure of O3. That's the ozone molecule. All right, so let's see if you were able to do it. So in this case, oxygen is going to do something kind of interesting. It's going to make a double bond to one oxygen and a single bond to another. And the way it's going to do that is do something known as formal charge. So let's look a little deeper at what this will end up doing. But first, if we know what the 2 possible resonance structures are, we can average them to get the overall structure. And so it is going to be a +1 up here, and it's going to be that negative oxygen on each end being shared equally, so -1/2. The average bond strength would be 1.5 because it's 3 divided by 2. So here you go. Here's your bonding structure, or your resonance structure for the ozone molecule. Again, remember that this is not an example of that double bond switching back and forth rapidly between the 2. They actually exist simultaneously. Resonance structures are also not isomers. Remember, isomers are different structures that contain the same number of atoms. So for instance, these are 3 isomers of carbon that all contain 5 carbons. All right, so take a look at this. Here is a drawing of the 3 possible resonance structures for nitrate ion, NO3 -1. Notice in all 3, there is a nitrogen that is positively charged in the middle, and we've got these 2 negatively charged oxygens on the ends. The overall charge is -1 because -2 and +1 equals -1. Okay, draw the resonance structure for the nitrate ion based on these 3 representations and calculate the average bond strength and the average charge on each oxygen. All right, let's see what you got. So this is what it should look like overall. We're going to take that double bond, we're going to split it among the 3 oxygens, so we're going to draw these dashed lines in between. The nitrogen remains +1 in all 3 scenarios, so its average charge is +1. There are 2 negative charges being shared among 3 oxygens, so we would say each oxygen has an average charge of -2/3. And there are a total of 4 bonds being shared among 3 oxygens, so the bond strength should be 4/3 or 1 1/3. All right, so let's see if you can do the resonance structures for sodium thiocyanide, SCN. Thiocyanide is a polyatomic ion, and what I want you to do is draw that together as an S, C, and N in that order. Try to bond everybody together. That polyatomic ion has a -1 charge. The sodium is going to have a +1 charge. So basically, you can think of it as sodium gave the electron to the thiocyanide. And let's see what you come up with. Pause the video, give it a shot. Okay, let's see what you did. So there's actually 2 different ways you could draw this. Version 1, you could put the sulfur double bonded to the carbon. That would satisfy sulfur's octet, and you could have carbon double bonded to the nitrogen. That would give 4 bonds for the carbon. The nitrogen only has 2 bonds, so it's going to get the extra electron that makes the polyatomic ion, and you end up with a structure like this. So basically 2 double bonds. On the other hand, you could have also have drawn it where nitrogen makes a triple bond to the carbon, and the carbon makes a single bond to the sulfur. In that case, nitrogen has the 3 bonds it wants, carbon has the 4 bonds it wants, sulfur only has 1 bond, so it gets the extra electron to satisfy the octet. So the question is, which one of these 2 is correct? And the answer is both of them are correct. In fact, they're both correct simultaneously because this is a resonance structure. So basically, that extra bond that's located right here, that SC bond, can either be here or it can flip to this side and become a triple bond. So the average bond strength is going to be 1.5 on this side. If I can draw that half, and it's going to be 2 and 3 divided by each other, so 2.5 on this side. Because it's either 3 or 2. As for the charges, it's -1/2 on this side and -1/2 on that side. And this shows the shape-filling model of those atoms. Okay, let's try the nitrite polyatomic ion. Nitrite is NO2 -1. So these are the 2 possible ways you could draw it. We know nitrogen needs to make 3 bonds. The oxygen can follow the octet rule by gaining that 1 extra electron that makes the ion. And so in this case, the half a bond on each oxygen, half a charge on each oxygen, -1/2. Average bond strength, 1.5. Okay, last one on here, the chlorate polyatomic ion. So I want you to figure out what the average bond strength is and the average charge of each oxygen in the chlorate ion. So chlorate, if you looked on your polyatomic ion sheet, is ClO3 -1. So in that case, you're going to draw this with chlorine having two double bonds for the two oxygens and a single bond with the oxygen that has the -1 charge. And then there's going to be a lone pair that's not involved. But which oxygen has the -1 charge is any of the three. So we're going to have to spread that out and rotate where those double bonds are located. Then we're going to take the average of all of those. So we've got a -1 charge spread out among three atoms. So we should end up with each oxygen having an average charge of -1/3. We're going to have 5 total chlorine-oxygen bonds, but divided by 3 oxygens. So 5/3 is the same as 1 2/3 is the strength of the bond. So this would be our overall resonance structure, where each of these represents 5/3 or 1 2/3, and then each oxygen is -1/3 in its charge. So those are resonance structures for you. All right, let's try bromate polyatomic ion, BrO3 -1. You can stop it, draw it, see what you get. Okay, let's see what you got. So this is one of the representations of the bromate polyatomic ion. As you can see, it's awfully similar to the chlorate polyatomic ion. That single bond could be here, here, or here. So in fact, and this negative charge could be here, here, or here. So in fact, the average is going to be a -1/3, -1 charge divided by 3 oxygens. It's a pretty bad 1/3, isn't it? And then that average bond strength is going to be 5/3 or 1 2/3. Okay, so that's resonance structures for you.